Today, I will be talking about the most beautiful equation in all of mathematics, Euler's identity. But wait, who exactly was Euler? And why is this identity considered to be so beautiful? Leonhard Euler was a Swiss mathematician who was born in 1707. He is known for founding the study of graph theory, solving the Basel problem, and giving a definition to the number e. In 1948, Euler published Analysis of the Infinite, where he describes Euler's formula, of which Euler's identity is a special case where x equals pi. Interestingly, although Euler's identity can easily be derived from Euler's formula, Euler never explicitly stated it in his work. Later, I will be explaining how we can prove that Euler's formula is true. In this formula, Euler uses the number e, which is known as Euler's number. However, he was not actually the person who discovered this constant. It was discovered by Jacob Bernoulli. He found that it was equal to the expression, the limit as n goes to infinity of 1 plus 1 over n, all to the nth power. You may recognize this formula from Unit 3, where we learned about how to calculate compound interest. Here, the limit is used to calculate the money that you will have after 1 year if interest is continuously compounded, with a starting amount of $1 and an interest rate of 100%. Bernoulli found that this limit was equal to approximately 2.718. But what is another way for us to express the value of e? Well, one way is by using an infinite series, known as a Taylor series. The expression for a Taylor series of a function is equal to the sum from k equals 0 to infinity of the kth derivative of x evaluated at the point a over n factorial times x minus a to the k. Here you can see an expanded version of this expression. So, using this formula, we can derive an expression which is equivalent to e to the x. E to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Similarly, there exist Taylor expansions for sine of x and cosine of x. Sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. And cosine x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. Now, you can probably see that these series all look very similar to each other. What can we do to make them equivalent? Well, if we add sine of x and cosine of x, we get 1 plus x over 1 factorial minus x squared over 2 factorial minus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial, etc. As you can see, this expression looks very, very similar to the Taylor series of e to the x, except the signs alternate every 2 terms. So, how do we modify these expressions so that they're equal to each other? Well, in order to change the sign on terms like x squared over 2 factorial and x to the 6th over 6 factorial, we would have to multiply them by a number which, when squared or raised to an even power, is negative, but no real numbers fit these criteria. Luckily, mathematicians have invented an imaginary number which does this, the number I, which is the square root of -1. So, rather than raising e to the x power, let's try raising it to the ix power and see what happens. Well, first of all, we'll get this series 1 plus ix over 1 factorial plus ix squared over 2 factorial plus ix cubed over 3 factorial, etc. Now, we can substitute these powers of I for their actual values. So, I to the first power is just I, and then I squared is actually -1, that's the definition of I. And I cubed is -I, and I to the 4th is positive 1. And then after that, it's kind of a cycle, so we repeat starting back at I for I to the 5th, I to the 6th is -1, etc. So now that we've done that, we can group these terms into terms without an I and terms with an I, so that eventually we can factor out the I. So yes, after we've grouped the terms, we kind of see a pattern that relates this series to our series for sine and cosine. So the series 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. That's actually equal to cosine of x. And those are the terms in our series which do not have an I. And then the expression ix over 1 factorial minus ix to the 3rd over 3 factorial plus ix to the 5th over 5 factorial. If we factor out an I from that expression, we will get I times sine of x, because the Taylor series for sine of x is x over 1 factorial minus x to the 3rd over 3 factorial, etc., etc. So we can prove Euler's formula using these infinite series, because we showed that e to the ix equals cosine of x plus I times sine of x. But what does this have to do with Euler's identity? Well, once we have the formula, deriving the identity is easy. All we have to do is substitute pi for x. So we get the equation e to the I pi equals cosine of pi plus I times sine of pi. And we all know from our studies of the unit circle that the cosine of pi is just -1, and sine of pi is just 0. So e to the I pi equals -1 plus 0, or -1. Therefore, e to the I pi plus 1 equals 0. So what's so great about this identity anyways? Well, the reason that it's thought to be so beautiful is that it relates 5 of the most important numbers in mathematics: e, I, pi, the number 1, and the number 0. Euler's identity also has many applications in complex numbers and trigonometry. With the formula, these identities can be derived. These allow us to find the complex number solutions to trigonometric equations. Thanks for watching, and I hope you learned a lot about Euler's identity.